Good day, I am Takis Villafranca, and today me and my groupmate will be presenting our support vector machine for the heart attack risk data PH. So firstly, we started by loading the dataset from the file itself into the pandas data frame, and then we showcased here the first 10 rows of the dataset to get an initial view of the data, which helps us in understanding the layout, column names, and spotting any immediate errors or issues.
In this part, we will indicate the structural information about the dataset we follow. This makes the output more readable and organized for the user. Next, the df.info function is called. This will provide a concise summary of the data frame, including the number of rows and columns, the names and data types of each column, the count of non-null values per column, and the total memory usage. This summary is useful for quickly assessing the dataset structure and ensuring all expected data is present. Finally, we'll check for any missing values using the df.isNull.sum. This returns the number of null or missing entries in each column. In this case, the output shows all values are present, meaning the data set is complete and ready to proceed for analysis.
So after that, since the dataset has about 1,000 individuals within the dataset, here we created a count plot that highlights who are at high risk with the heart attack distribution. So as you can see, there are a lot of individuals who are not at risk, and there is about less than half who are at risk. So in short, we created this count plot to give us an overview of why we are doing the sport vector machine in the first place.
In this part of the code, we prepare the dataset for training a machine learning model to predict heart attack risk. We start by separating the data. The features or input variables like age, cholesterol, and blood pressure are stored in X. The target variable, whether someone is at risk of a heart attack, is stored in Y. Next, we split the data into training and testing sets using an 80 to 20 ratio. That means 80% of the data will be used to train the model, and 20% will be used to test how well the model performs. To make sure each group has a balanced mix of risk levels, we use stratification based on the target variable, and then we check the shape of the data to confirm everything is split correctly. 800 rows for training and 200 for testing. Finally, we standardize the data. This is an important step because some machine learning models work better when features are on the same scale. Using the standard scaler, fit and transform the training data, calculating the mean and standard deviation, and applying the scaling. Then we apply the same transformation to the testset with the learning from it to prevent any data leakage. This prep processing ensures the model can learn effectively and be fairly evaluated on unseen data.
Now we move on to the hyperparameter tuning for SVM models. So to improve upon heart attack risk prediction, grid search CV with a five-fold cross-validation was used to tune the linear, RBF, and polynomial SVM models, wherein recall was the scoring metric with class weight equals balanced to address was used to address class imbalance. Then over here is the linear SVM optimized for the regularization parameter C to balance out margin size and classification accuracy. Next is the RBF SVM tuned for C and gamma to capture nonlinear patterns while maximizing recall. Polynomial SVM, which explored combinations of C, degree, and gamma to model out complex relationships and improve upon high-risk case detection.
In this section, we're testing different types of support vector machine models to find the one that best predicts heart attack risk. We start by creating a dictionary of SVM models, each using a different kernel. Linear kernel for straight line separation, RBF for more flexible curved boundaries, and polynomial for more complex, multidimensional separation. Each model is configured with specific settings like regularization strength and class balancing to handle uneven class distributions, important in health data where high-risk cases may be fewer. The code then loops through each model. It trains the model on the training data, predicts outcome using the test data, and finally, prints performance metrics like accuracy, how many predictions were correct overall, precision of all predicted high-risk cases, how many were truly high risk, recall of all actual high-risk cases, how many the model correctly identified. This last metric, recall, is especially important in medical applications because missing a high-risk patient could be dangerous. By comparing these models side by side, we can choose the one that performs best for this higher attack risk classification task.
Now we move on to the visualizing part of the SVM decision boundary for linear kernel. So to illustrate how a linear SVM classifies individuals based on age and cholesterol, the model was trained on scaled data with class underscored weight is equal to balanced. A mesh grid was created to simulate input space and predictions were used to plot the decision boundary. The resulting plot highlights classification regions and overlays actual training points, helping visualize how the model separates high and low risk individuals in 2D.
This part is the code we use for visualizing the decision boundary of the RBF kernel. This plot shows how an SVM with an RBF kernel tries to separate patients by heart attack risk based on age and cholesterol. The background colors red and blue show the model's predicted zones. The dots are actual data points, red for high risk, blue for low risk. We can see a lot of overlap, meaning age and cholesterol alone don't clearly separate the two groups. The wavy boundary shows the model is flexible, but the features might not be strong enough for accurate predictions on their own. This part is the code we use for visualizing the decision boundary of the polynomial kernel. This plot shows how an SVM with a polynomial kernel tries to separate heart attack risk using age and cholesterol. The model creates a complex, star-shaped boundary, but the red and blue dots still overlap, meaning these two features alone don't clearly separate risk levels.
For the final part, we combine the different decision boundaries of the SVM kernels that were trained on scaled age and cholesterol features for a more clear comparison on how they classify data using a mesh grid. As you can see, each subplot displays the classification regions and training data, revealing how the linear kernel creates straight boundaries, the RBF kernel forms flexible nonlinear regions, and the polynomial kernel captures more complex patterns. This visual comparison highlights the varying capacities of each kernel to separate high and low risk individuals from heart attack.